Thank you, Jean-Baptiste Masson. I think you said almost everything, so I could be very short now. I am very happy to give this keynote address at this graduation ceremony. I must say that the graduation ceremonies are not so much in the habit of the French universities. I see the first time I'm attending such an event here, and so I want just to salute the graduates. I see that you don't have a cap or a hat, as it is usually the case, but just a scarf. And this might be maybe more comfortable if you have to dance later on in the afternoon. But I think it's a habit that maybe other universities should resume. It's very important to have a kind of symbolic event at the end of this stage of your career. When I was asked to give this talk, I wondered why a physicist is asked to give a talk at the graduation ceremony for an institute which is mainly working in biology. And of course, there are connections between physics and biology. Some of the tools which are being used to probe biological systems are coming from physics, and also some of the methods, some of the models that you use in biology comes from physics, in part statistical physics. But I think it's not the main reason. I think there is a deeper reason for that, and this, I think, comes from the fact that you started doing research, going into science, because you were driven by curiosity. You wanted to do things, to be in the process of creating knowledge for the sake of it. And it was the same when I started my career in science more than 50 years ago. I was driven by curiosity, by the need to understand the world around us, to unravel the mysteries of the world. And when I say mystery, I don't mean to talk about something which is marvelous, which cannot be understood in a rational way. I think about mysteries of things which are hidden in nature, which are sometimes counterintuitive, and which you discover with rational thinking. And I think this is very important, especially nowadays when truth, not only scientific truth, but truth in general, is under attack. And for example, in your field, there are a lot of people who say that vaccination is dangerous and should not be used, and this is only an example. There is in chemistry and in physics also a tendency of fake news, of false information, and I think we as scientists, whichever the field in which we are working, are here to testify about the value of the truth, which is based on observation, and from observation, the building of models which are subjected to the administration of proof. And I think this is something very important. I will come back to this at the end of my talk. But what I wanted to tell you today is to describe a little bit my scientific career, to try to illustrate some of the points I would like to make. I would like to start by discussing why I became a scientist. And I'm very often asked the question, when did you decide that you wanted to do science? I just want to say that in my childhood and as far back in the past that I can remember, I have always been interested in the observation of natural phenomena. I remember when I was a child, I was comparing the specific masses of different metals, from very light metals like aluminium to the heaviest metals like uranium. And I was surprised that the same volume could have so much different weight, and of course it is related very closely to the increase of the atomic masses, and this was a puzzle for me. I was also interested in the properties of light, the fact that the diffraction of light when it comes into water, and the fact that when you look at your feet in water, they seem to be closer than when they actually are. So all these things were surprising me. And when when I was 12 or 13 years old, I was offered a book in astronomy. It's called Astronomie Populaire by Camille Flammarion, which was first published at the end of the 19th century, and which in the 1950s describes the world, the universe as it was understood then, which is rather close to what we know now, but much less precise, of course. And I was fascinated by the description of the planets. I saw the beautiful pictures of planets which were looked at through telescopes, pictures which are much less startling than the one we have now, which are taken by spacecrafts, which are getting very close to them. But still, I found this very fascinating, and I used to make classification of the planets according to their masses, to their volumes, and to their orbits, and kind of drawings that you can see here. And this was I was really fascinated by the size of the universe that you can discover just by looking at these planets. And this book was also describing the lives of the great scientists who have made the planetary system understood. Of course, Copernicus was the first to displace the Earth from the center of the universe, and who made the first great discovery which shows that what you think, what the illusion you have about the world is wrong. The fact that it seemed quite obvious that the sun was going around the Earth, but in fact it's the other way around. This is one of the mysteries I was talking to you about at the beginning. Of course, after Copernicus, you had Kepler, who made meticulous measurements of the position of the planets, and from that discovered that the planets were going around ellipses, and that you can relate the period of the planet with the radius of the ellipse. Galileo was another hero who observed through his first telescope Jupiter and his moons, which was the first example of a planetary system which vindicated Copernicus' ideas, and which Galileo did at the sake of his own freedom, because this was supposed to be anathema at that time. It was completely contrary to the beliefs of the church. And of course, the last one was Newton, who, with his theory of gravitation, was able to unify the fall of an apple on the Earth and the motion of the planets, and shows that mathematically it was possible to discover, to explain Kepler's law. And of course, these are great luminaries, and it's impossible to compare oneself with these people, but there was another guy who was described in this Astronomie Populaire, which I found also very interesting. It's the French astronomer Le Verrier. Le Verrier was in the 19th century looking at the trajectory of the orbits of the planets, and especially the last planet which was known at that time, which was the planet Uranus. And he found that this planet did not follow exactly Kepler's law. There were small perturbations which were due to the effect of the other planets. And when he included the perturbation of all the other planets known, like Saturn, Mars, and so on, he still had a small discrepancy. And he attributed this discrepancy to an unknown planet, which was beyond Uranus, and he indicated where this planet should be, and when the astronomers aimed in this direction of the sky, they found Neptune. And I was fascinated by the fact that mathematics was able to predict things, not only to explain things which are already known, but to predict new things. And this fact that mathematics explains the world is something which has really struck me since then, and which is still fascinating me today. So I just decided that I wanted to be an astronomer, to go into astronomy, to use mathematics. And since I was good at school, when I finished the baccalaureate, I went to the Lycée Louis Grand, where I studied in the preparatory school, the classe préparatoire, and I passed the examination of École Polytechnique and École Normale, and I was received at the École Normale when I started really my life as a physicist. At that time, just before that, at the end of the 1950s, the Sputnik and the race to the moon started, and I was fascinated also by that, the fact that the knowledge in astronomy can also be complemented by technology, by the fact that we could really go there and observe this closer. And with the amount of mathematics I had, already in high school, in the 10th grade, in classe de seconde, I was able to compute the trajectory of the satellites and the escape velocity which was required to go to the moon. So this was again proof that mathematics could be used in simple terms. I am afraid to say that I think that now in the modern programs of high school, I am not sure that the students in classe de seconde are able to do this kind of calculation. They know a lot about qualitative ideas about physics, but to do calculation really and to use maths to do that is something which is lacking now, and this is one problem. But so I eventually entered into École Normale, and of course at the beginning in this school, life was fantastic. It was very different from the strenuous and stressing years of class préparatoire. In the first year, you can decide what you wanted to do, attend or not attend lectures, discuss with friends into this inner courtyard, which looks very much like a yard into English, Oxford or Cambridge College. And so I enjoyed this freedom very much. And I still did not know exactly what to do. What I want to say, since we are here at Institut Pasteur, is that one of our prestigious predecessors in École Normale Supérieure was Pasteur. He was a Normalien back in the 1840s, and you see here his picture taken from an old photograph, daguerreotype, and you see it was a very serious man. It's very far from the iconic image of Pasteur in his latter years with his beard, but he was already very serious, as you can see here. After he left École Normale, he was appointed in some universities in France, and then he came back 10 years later as Directeur des études. So he was mentoring and following the young students in the École Normale, and I must say that he did not leave a very good memory. He was very unflexible. He was always enforcing a very rigorous discipline, and the Normaliens who are used to more flexibility were not very happy about him. But he did some very good work at that time. At that time he was more like a chemist, and he discovered chirality, the fact that molecular structures can take two forms which are mirror image of each other in a mirror, and that the left and the right form have different optical and chemical properties. And of course, chirality plays a very important role in biology, and it plays also an important role in physics. A few years before I entered into École Normale, at the end of the 1950s, it had been discovered that the left and right images of a physical process were not equivalent, that the physical process taking place in real natural conditions, when you looked at it through a mirror, gave a process which did not exist. This is called parity violation, and it plays a very important role in particle physics. I just discovered that at that time. I understood that Pasteur was already a precursor in this area too. So I still trying to get into astronomy. I went and visited the Nancy Observatory, which is a radio observatory in the south of Paris, which was managed then by people from École Normale, and I just considered entering into this field of science. But then I was driven in another direction, and I went, instead of trying to understand the world of the infinitely large system, the universe, I went into the infinitely small system, which is properties of atoms. And I want to try to explain why I made this change. In fact, the lectures I got in the first year and second year at École Normale were given by Kastler and Brossel and Cohen-Tanucci, and they were dealing with atomic physics. And at first I saw that there was not so much difference. After all, we know from high school that an atom is a kind of planetary system, a positive core, which plays a role, nucleus, which plays the role of the sun, and electrons going around, which obeys to the same kind of law as the planets. But of course, I learned that in the microscopic world, the particles obey the strange law of quantum physics, which are very different and very counterintuitive, very different from the laws which explain the behavior of planets. The first thing we can say is that the electrons can occupy only quantized orbits, so only orbits which are labeled by integral numbers 1, 2, 3, and nothing in between. And for an electron to change orbit, it has to do what is known as a quantum jump. It jumps from one orbit to the other in a random, instantaneous process. And this quantum jump occurs by the emission, is accompanied by the emission or absorption of a quantum of light called a photon. And this quantum of light is like a small wave packet which is emitted or absorbed by the atom. And this wave packet has a wavelength and a frequency, which is related to the color of the light. As you know, the wavelength decreases when you go from red to blue, and the frequency increases when you go from red to blue, because the frequency is inversely proportional to the wavelength. And so, by looking at the photons which are emitted during a transition, their frequency is proportional to the energy difference between the two orbits. The energy difference E being equal to hf, where f is the frequency and h is the constant that Planck introduced at the beginning of quantum physics, called the Planck's constant. So if you measure the frequency of light, which is emitted or absorbed by atoms, you know the structure of the energy levels, and this is known as spectroscopy. This is the science, the art of measuring the frequencies of the light absorbed or emitted by atoms. And this science, in fact, was the origin of this science can be traced back again to the great Newton. Newton is the first physicist who showed that white light, the light of the sun, can be dispersed in all colors, going from the blue to the red in a rainbow of colors. And you can see that if you send white light through a prism or through a more complicated, more sophisticated spectrometer. And so if you send this white light through a gas which contains atoms or molecules, the frequencies corresponding to the transition will be absorbed, and in absorption you will see dark lines in the continuous spectrum. On the other way, if you excite atoms and look at the light they emit, you will see bright lines which correspond to the fact that the atoms will jump from an upper level to a lower level. So dark lines or bright lines are a signature of the element that you are looking at. It's like a kind of barcode, the same kind of barcode that you have in all supermarkets now, which design specific elements. And you can look at the light coming from the stars, and then I come back to this astronomy ideas that I got from the Flammarion book. If you look at the spectrum coming from the sun, the solar atmosphere, or from stars, faraway stars, you see lines corresponding to elements that we have on Earth. For example, you see calcium lines, which are created, calcium atoms which are produced by nucleosynthesis in stars. And these are the same lines that you find if you take a bone and you crush the bone and look at the light, at the spectrum. If you put this bone in a flame, you see the same line, so it means that the same element exists everywhere in the universe. What I learned also is that these spectra provide information, of course, about the structure of the electron in an atom, and the careful study of the spectra was the way quantum physics was born. In fact, it is by analyzing the spectra that more and more sophisticated results were obtained, and the principle of quantum physics emerged from a long process at the beginning of the 20th century with the study of more and more complicated spectrum. There is another interest of these spectral lines. In fact, the wavelength or the frequency of an atomic transition or a molecular transition are perfectly well defined anywhere in the universe, and you can use them as standard. A wavelength is a standard of length. If you can define the meter as a given number of wavelengths of a given transition. And this is the way the meter was defined back in the 1960s when I was a student. And also, if you can measure the frequency of an atomic line with precision, if you lock a source of light to this line, you have now an electromagnetic wave whose period is the ticking of a clock. Atomic clocks are based on that, and very precise atomic clocks can be built on this system. So you see that spectroscopy is at the same time a basic physics and applied physics. And I just say a few words about the people who introduced me to that. You see here Alfred Kastler and Jean Brossel, who were the head of the lab, and they taught, Kastler was teaching us atomic physics. He gave a kind of poetic description of atoms and the way atoms interacted with a kind of semi-qualitative description of the way atoms interacted with light. Brossel described in great details great experiments which have made us understand quantum physics, and Claude Cohen-Tanucci, who had been the student, thesis student, gave a very, very beautiful theoretical description of quantum physics, explaining what Kastner was saying in more qualitative terms, and also what Brossel was telling us. So, and it has been recorded that Kastner and Cohen got each of them a Nobel Prize. They not only taught spectroscopy, but I learned from them that spectroscopy could be used not only to explore the energy level of atoms, but also to manipulate atoms. If you shine the right kind of light on an atom, you can change its velocity, you can change its angular momentum, its magnetic moment. You can put it in exotic states, which are very strange and had property quite different from the one we're used to. And this is the kind of things that I've been doing since then. The first method to change the properties of atoms using light was called optical pumping, and this is a topic on which Kastner and Brossel worked. So these in fact are the people who made me change from astronomy into atomic physics. And this is a picture which Jean-Baptiste referred to, so I can go very fast on this picture, and I just want to tell you that I have extremely good memories of that time. It was a small lab. The Kastner and Brossel instilled in this lab the spirit of freedom, of creativity. We were able to work without having too much money, but we were free to do the kind of things that we wanted to do. We did not have to publish. We were not under the pressure of publishing every day. We did not know what a citation index was. And this was very, really refreshing. And I think it is because of this atmosphere that this relatively small lab was able to have one Nobel Prize per generation from the 60s up to now. So I just wanted to recall that. So just in case you don't recognize. I must also say something about luck. Luck is a very important element when you do research. And I have been lucky to start in science at a time when an extraordinary tool was invented. I'm talking about the laser. Until 1960, light was just the light that you get from the sun or from lamps, and it's a very, very chaotic light. The lasers changed that completely, and they gave rise to very well-collimated beams with having a very precise direction, very precise frequency, very precise phase, and all this clearly was going to open a new domain in spectroscopy and beyond spectroscopy in physics in general. And we had the intuition of that. We did not know what the laser would bring exactly, but it was clear that it was really exciting. And I remember at that time I had a lot of fellow students who were making fun at me, saying, why are you going into spectroscopy? Spectroscopy is boring. You're just recording spectra, you make tables of wavelengths or frequencies, you put that in books and so. And it's much more exciting to go in condensed matter physics or to go in particle physics and so on. But because I had, and Claude Cohen-Tanucci had this intuition that lasers were going to change the scope completely, I stuck to atomic physics and I don't regret it. So, but I had to be trained in this field. So on this slide, I just show you very quickly what are the differences. In an ordinary lamp, the atoms are emitting independently from each other. Each atom emits a photon in a given direction with a given frequency or phase, so it's just random light. In lasers, the atoms are made to emit in step. They all emit in the same direction with the same phase and same frequency. So I would call this tamed light as opposed to the wild light of classical sources, and this is what makes the difference. So I wanted to tame the light, and for that I had to go in a place where people used to tame the light. And I went for my postdoc to Stanford, because Stanford, it was not yet Silicon Valley, but it could be called Laser Valley. It was a place where the new companies were building the first tunable lasers, lasers in which just by turning a knob, you can change the frequency of the laser, which is essential if you want to do spectroscopy. So I went into the lab of Art Shallow, who was one of the fathers of the laser, and Shallow had just hired a new associate professor, Ted Hench, and you see them in this picture. Ted Henge is a kind of wizard, genius of lasers. He kept inventing new methods to use lasers to do precise spectroscopy. And so this year was a fantastic year in which I discovered a lot of things about lasers. And I made a good friendship. I have been a friend with Charlot until he died in 1999, I think. And I'm still a very good friend of Ted Henge. And they both went to get a Nobel Prize for different aspects of laser spectroscopy in the future. So I learned how to work with dye lasers, and these lasers have been very important in the first stage of my career, and tunable lasers in general. So I want to say a few words about my own research. Before that, I want to insist on another point, which is very important. When you do research, when you are a scientist, you have a big privilege. You have the privilege not only to do your own research, but also to witness what other people are doing, not only in your lab, but in a worldwide community. And I just want on this slide to just give you a glimpse of what lasers have permitted, what lasers have made possible during the last 50 years. Of course, we all know that lasers are everywhere in technology. You use lasers to read CDs and DVDs, barcodes, to do surgery and so on. But I want to focus on laser in basic science. And what I want to show you here is that about 10 orders of magnitude have been gained in different directions. And this is a huge improvement. 10 orders of magnitude means a factor of 100 every decade. So what can we discuss? The first thing is spectroscopy, precision spectroscopy. Before the advent of lasers, when you measured an atomic line, if you could put 6, 7, or 8 digits in the measurement, it was a tour de force. Now, with lasers, you can measure atomic lines with 18 digits. So it's a 10-order improvement. Now, if you use this line to lock a laser, to lock an electromagnetic source, to make an atomic clock, you see that you win these orders of magnitude. In the 1960s, the best clocks were quartz clocks, and they had a precision of 1 part in 10 to the 8, which is 1 second per year, which was supposed to be fantastically good. Now we have clocks which keep the time within 1 second in the age of the universe, 1 second in more than 10 billion years. It means that if you just synchronize two clocks, they would not drift apart from each other by more than a second in billions of years. And of course, precise atomic clocks are essential for the GPS system. But the GPS system is based on clocks which are 4 orders of magnitude less precise than that. So it's I leave to your imagination what could we do with a GPS system which would use clocks 10 to the 4 orders of magnitude more precise. The second direction I want to discuss is the sensitivity of measurements. When I did my experiments, I was using classical light to be absorbed or emitted by samples, the gas, which a few cubic centimeters, which contain billions of atoms. So the information I could get was statistical. I could just see statistically what was going on in the gas. And for example, it was impossible to see quantum jumps, because when an atom was jumping, he was jumping in the middle of billions of other atoms, and so you just saw an average effect. Now, with lasers, you can see single atoms and single photons, and I will come back to this later. But let's go in another direction, low temperatures, the kind of physics that Claude Coyne-Telgy did for the remaining 20 years after I stopped working with him. In 1960s, cryogenics, the art of going to low temperature, was limited to 1 Kelvin or maybe 1/10 or 1/100 of a Kelvin, which is an absolute degree of temperature. And it was very cumbersome. You need to have huge cryostat with helium and so on. Now, if you use lasers, properly tuned lasers, you can cool atoms, you can reduce their velocity to temperatures which are unbelievably cold, which are smaller than 1/100000th of a single Kelvin. At these exceedingly low temperatures, the atoms are creeping, are moving at velocities of the order of millimeters per second or so, and if you don't keep them in a trap, they just fall. And so you have to keep them, and at this very low temperature, new phases of matter appear, new quantum phases of matter, which are very interesting fundamental and applied properties. Another direction, time resolution. If you want to study a fast phenomenon, you use stroboscopy, that is, you send pulses of light and you see how the system moves from one pulse to the next. But the length of the pulses, back in the 60s, was microsecond, or maybe in the base case, a few nanoseconds. Now, with lasers, you can make pulses which last 1 attosecond. An attosecond is a billionth of a second. And if you shine a succession of pulses like that, you can see the motion of electrons in atoms, or the vibration of molecules, or chemical reaction as they proceed. And it might also be very important to study some biological processes. The last direction I want to discuss rapidly is the sensitivity to displacement. You know that you can use lasers to measure distances. You see that geometers have a laser in their pocket, they shine the laser on the wall, and looking at the light reflected, they know the distance to the wall. But this can be brought to an exceedingly high precision. If you send a coherent beam of light, which has a well-defined phase, reflect it on a mirror, and make the reflected beam interfere with the outgoing beam, you can measure very, very small shifts in phase, which allow you to measure the displacement of a mirror of 10⁻18 meters, which is 1/1000th of the size of a single atom. And this is this kind of precision which is used in the gravitational wave antennas. Hugely, very powerful lasers propagate along kilometers in evacuated tubes. They are reflected on mirrors. The light is recombined, and from that you can see the effect of the passage of a gravitational wave produced by the collapse of two black holes billions of year lights away from the Earth. Einstein, in the 1950s, of course, this was impossible. The best precision you could have was 10 orders of magnitude lower. And so Einstein could never have believed at the end of his life that the verification of the gravitational general relativity theory would be possible ever. And in fact, what I want to say also is that this experiment is a fantastic combination of two fundamental discoveries by Einstein. In 1916, he produced the theory of general relativity, which predicted the existence of these waves. And in that same year, he wrote a paper on stimulated emission of light by atoms, which was a seminal paper for the discovery of lasers 40 years later. So in fact, in the same year, he gave some hints about the theory which produced this wave and the technology which makes the detection of this wave possible. But Einstein had no idea about that, and this is another very big, interesting fact about basic science. You do it just because you want to understand, but you don't have in mind the logical consequences and all what can be done with your invention. But the kind of physics I'm doing myself is related to the sensitivity of measurement, the fact that you can observe single particles. And I just show you here on this slide a picture which shows 5 beryllium ions. An ion is just an atom in which you have removed an electron, so it has a net charge, and you can use electrodes which produce electromagnetic fields which trap the atoms in space. So now, since these atoms have the same charge, they repel each other, and they take an equilibrium position which results from the attraction at the center of the trap and the repulsion, and you have this kind of strings of atoms, this kind of small unidimensional crystals. Each atom looks very bright because you shine the light with a laser, you need a laser for that, which has very precisely the frequency to excite the atom. The atom is excited, then it re-emits a photon, you re-excite it, and the cycle can be repeated millions of times per second, which means that a single atom will shine millions of photons into your eye or into a microscope, and you see each ion as a bright spot. And this was produced in the lab of Dave Wyman, who got the Nobel Prize with me in 2012. There have been progresses since then. You see strings of 14 or 30 ions. Each ion can be addressed individually. Moreover, the ion can be brought in different states. In one state, the ion will scatter light, appear very bright. But if it goes to another state, which cannot absorb the light, it will become dark. You won't see it anymore. And you see that you can observe, if you look at the light intensity, you can see the quantum jumps. When the electron leaves the state which can scatter light, the light goes to zero, and later on, the atom comes back into this state and the light comes back. And these quantum jumps are now a standard method to find out whether the atom is in one state or the other. Now, a two-state system carries a bit of information. You can say you have 0 if you are in one state, 1 if you are in the other state. If you have a string of 30 ions, the number of states which are available is 2 to the 30. 2 to the 30 is close to 1 billion. So you see that this chain of 30 atoms can contain information corresponding to 1 billion bits, 1 billion different quantum states. And if you play with that and get the atom interacting with each other, you have a kind of abacus which can give you some ways to process information using quantum physics as quantum logic. And this is the field of quantum information science. I'll just say a few words about that to conclude. But now to connect to my own work, I show you on this slide the difference between the work of Dave Whelan and mine. In fact, there are the two sides of the same coin. In Dave Whelan's lab, he is trapping atoms, which are the object of investigation, and using light to probe the atoms. And in Paris, we do the opposite. We trap the light in a box that is in a cavity made of two highly reflecting mirrors, and we send atoms one by one through the box to manipulate the field in the box and to detect the photons. And I must say that, which was mentioned by Jean-Baptiste in his introduction, we do it in a non-destructive way. The atoms are not destroyed when they are measured, and even more difficult, the photons are not destroyed. Usually when you detect photons in your eye, for instance, the photons are destroyed on your retina or on the photocathode. Here, the photons are just observed because the atoms can extract in a very subtle way information from the field. And this is, of course, a domain of research which is performed now in the world, the goal being to develop quantum information. So a few words about quantum information. This experiment illustrates the strangeness of quantum physics. And this strangeness can be defined by two properties. The first one is state superposition. State superposition means that if a quantum system can be in two different states, classical state, for example, an atom in two different positions, it can be in these two states at once. It's not like in classical physics. For instance, an atom can cross a screen where you have made two holes by the two holes at the same time. And the second property is called entanglement. It means that if two quantum systems have interacted, even if they are separated by a large distance, they remain an influence of one system with the other, and if you make a measurement of one system, it has instantaneously an effect on the statistic of measurement you can perform on the other. These two notions have been summarized by Schrödinger in his famous tale, Schrödinger's cat. You may have heard about it. It has nothing to do with biology. It just means that his idea is to put in a box a living object, very complicated, a cat, with a single atom. If the atom is excited, nothing happens to the cat. If the atom goes into a lower state, it emits a photon which triggers a process which kills the cat. Now, if the atom is in a superposition of being excited and not excited, then the cat should be in a superposition of being dead and alive. So, of course, nobody has observed that with a real cat, because this strange logic is at work in the microscopic world, but all these properties are usually veiled when you go to the macro world by a process called decoherence, loss of the quantum coherence in large systems. So if you want to observe this, you have to manipulate isolated quantum systems, single atom or single photons, and this is what we do in our experiments. So the question next is, why are we doing that? Why is it important to manipulate isolated quantum systems? The first answer, and we always come back to the same idea, is it is curiosity. Is it possible? Can we do that? And if we go to single atom and single photons, will we see what quantum physics predicts? Is quantum physics a statistical theory, or does it apply to single objects? And in fact, the answer was not obvious. Schrödinger himself did not believe that this experiment would be possible. And I just quote here one of his famous sentences, which he said back in 1952, so quantum physics was well established. We never experiment with single electrons, atoms, or small molecules. In thought experiments, we assume that we do. It always results in ridiculous consequences. So our challenge was to prove Schrödinger wrong, to prove that Schrödinger's intuition of this was wrong and that the consequences were not ridiculous. So we tried to get into this by doing experiments involving less and less atoms, less and less photons until we get to a single one. Now, the reason why we want to do that also has a technological aspect. You all know that Moore's law, that the power of computers keeps increasing just because you can pack more and more transistors in smaller and smaller volumes. In fact, you can code a bit into a transistor, and now transistors are just imprinted on circuits, on microcircuits, and the density of transistor is such that each of transistors has now the size of a few atoms. And we reach now the limit of Moore's law. We cannot go smaller than one atom. So if we want to go further, the only solution is to exploit quantum logic, to prepare our system into strange quantum states, state superposition, Schrödinger cat states, and in this case you can escape to the fact that the classical Moore's law gives you a limit. So this is one of the reasons why these experiments are being carried and being financed. So just a few words about the tools that I use in my experiments. The atoms that I use to probe my photons are not just regular atoms, and this is where the laser comes into play. I am working with very excited atoms, which have very exaggerated features. They are called Rydberg atoms, from the name of the Swedish physicist who found the formula which gives the spectral lines. In fact, what we do is that we start from an ordinary atom, and with a laser, we excite one electron to a huge orbit, which is 1,000 times larger than the natural orbits. And so we get an atom which is very, very big, which is its size of the order of fraction of a micrometer, a kind of biological size, and no longer an atomic size. And this very, very far electron, which is very far away from the core, is very weakly bound. So it is subjected to perturbation very easily. A very small perturbation, another atom passing by an electromagnetic field will change slightly its frequency. And here we come back to the idea of Leverrier. The planet Uranus had a huge orbit very far from the Sun, which explains that it was sensitive to perturbation. Here, our outer electron is like Uranus, and the perturbation we want to observe are like Neptune. And what we found just by chance is that these atoms were exceedingly sensitive to microwaves, and that eventually we could reach the point where a single atom interacting with a single microwave photon would be observable, and this was the end of this quest. So you see, this system is like hydrogen, and again it's something which looks like an astronomical system. So what we did is just summarized here. We send Rydberg atoms through a cavity made of two highly reflecting mirrors, one atom at a time, and these mirrors are exceedingly good. In fact, they are so reflecting that light can bounce more than 1 billion times between the mirror before being lost. So thousands of atoms can cross the cavity one by one, and each of them can extract some information and can follow the evolution of the field in the cavity. So you have these small movies shows a little bit what we are doing. And I don't want to describe the experiment, I will just give you an example here. We are able to prepare in the cavity a field which has at the same time two phases. You see these two sine waves are opposite in phase. The field is at the same time with the upper phase and the lower phase. Or we could have a field which is at the same time with a high amplitude and a small amplitude. And this, we could study the superposition and study how they lose their quantumness as time goes on, how the phenomenon of decoherence destroy this quantum phenomenon. So at the end of my talks, I usually ask the question, but when will the quantum computer arrive in this picture? Quantum computers are, of course, the holy grail of people working in quantum information. So it will be a kind of huge Schrödinger cat which will be tamed to compute on different passes at once. And in the end, all these passes will interfere, and you will make a measurement which will provide the result that you want to get. So this is the idea, but decoherence, which destroys the quantum coherence very fast, is of course the enemy, and we have to develop procedures to prevent the system from decohering. I don't have time to discuss that. We have also to find the good quantum system. Would we carry the information on atoms, or on photons, or on some other kind of quantum systems? We have to invent also useful quantum algorithms to take advantage of that. And just what I want to say is that a lot of experiments in theory remain to be done, and the quantum computer is still an utopia. I'm not sure at all that it will come of age, but what I'm sure is that the research in this direction is going to bring some surprises. So this teaching about quantum information is what I did during the last 15 years before I retired, and I just want to say a few words about Collège de France, which was mentioned. So at the beginning of my career was École Normale, which was a very old institution, but the Collège de France is still much older. Collège de France was created by Francis I in 1530, and you see this picture shows a kind of historical rendition of Francis I signing the decree which founded the Collège de France, presented to him by Guillaume Budet. And this is a place, as Jean-Baptiste has said, which professors lecture about the research that they are doing in all fields, humanity and science as well. And among the famous professors of Collège de France in the 19th century, you had Jean-Paul Lyon, who deciphered the Rosetta Stone. You have Ampère, who was one of the pioneers of electromagnetism with Faraday. You have Claude Bernard, who was one of the founders of experimental medicine, and Henri Bergson, who was a philosopher. Surprisingly, or not surprisingly, Pasteur was not a professor at Collège de France. I don't know whether because it was too much involved into the Institut Pasteur and was not so much interested in teaching, or maybe because he was in some kind of competition with Claude Bernard. And this has happened in the history of the Collège de France. When you have one very strong person in one field, it's difficult to have another one. Physicists would say that the professors are fermions. They just, two of them cannot exist in the same state. So maybe Pasteur was an example of that. Also, I have seen on the site of the Institut Pasteur that this institution boasts itself to have 10 Nobel Prizes. So it's the same for the Collège de France. There have been 10 Nobel Prizes in all fields. And of course, there have been very strong ties during the whole history between Collège de France and Institut Pasteur. And 3 of these prizes in biology, Monod and Jacob have been professors at Collège de France and have been here. Nicole, I think I found on the internet that Nicole was never a member of Institut Pasteur, but he was studying at Institut Pasteur at the beginning of his scientific life. So I think it's time to conclude, and I would like to say a few things to keep in mind about science that I have tried to illustrate in this talk. And for each point, I will have 2 key words. The first key words are freedom and trust. And good research requires the right environment. The trust from the institution which allow the scientists to choose freely the topic which excites them. And this is exactly what I found at Laboratoire Castel-Brossel when I started. The second key words are time and patience. It takes a long time to develop ambitious projects, and you make a lot of trials and errors. This cannot be optimally pursued with a succession of short-term grants. You need to have a continuous source of money which allow you to work without having to produce quickly a result. And of course, the expertise should be passed from one generation of students to the next with permanent people, which can really provide a good basis for research to be continuous. The third point is luck and intuition. As I said, you need luck at some point. I have had many times luck, and of course, when you encounter something unexpected, you have to decide whether it's something interesting or just an artifact. So then you need intuition. Intuition has to tell you whether you had some luck or just some thing which happened by chance. And the last point is honesty and responsibility. You have to publish your result as clearly as possible so that they can be reproduced. And there have been examples, unfortunately, in recent time where this has not been always followed and has led to a lot of problems. You must not oversell your work and make false promises. So I never say that what I'm doing will lead to a quantum computer, even if I am very strongly pushed to say that by various people. So you have to keep this in mind. And of course you have to try to explain your science to the layman, because after all it's the citizen who pay for your research, and also because you have to explain them what science is about. And I come back to the point I raised at the beginning of my talk. You have to explain because you have to give the feeling, you have to make people understand that science is important and science carries values which are important beyond science itself. So with that, I just also want to add a last point, which of course you don't work alone. And my research has been carried out in a group whose size you can see here. And I've worked for many, many years with two senior colleagues, Jean-Michel Raymond and Michel Brune, who had been first my students and became my collaborators and co-workers. And this picture was taken on the roof of the Collège de France building. And we like to work in this environment. We see some cultural points here, and I think it's very important to associate not science with culture and with humanities. And the last picture is a picture which was taken in Stockholm in 2012. I am with my David Wineland, who is a colleague and a friend of many, many years. And I want just to insist to stress the fact that you can compete friendly with people. And when you do that, it's really a big gift. And I am a friend with all the people in this picture, of course, with Michel Brune and Jean-Michel Raymond, and with Dave Whelan, and Dave knows them also, and I know the people working in Dave's group. So I wanted to finish on this positive note, and I thank you for your attention.
Thank you very much, Professor Haroche, for this inspiring talk. So now there is time for a few questions. Somebody has something to ask Professor Haroche.
Thank you very much for the talk. I'm wondering, so during work on a particular project, you always have some interesting results, which kind of distract you from the main direction. To what extent would you spend time on these interesting results, which finally can become artifacts, or on the main project?
No, I think you are right. There's unexpected things that you want to pursue on the side, and we all often do that because there's one point, of course, I didn't mention. If you have students, even postdoc coming in your lab, the student, the postdoc cannot wait for decades to get a result. So you have to be able to divide a project into slices, into smaller projects. The problem is that they should not distract you too much, and you should try to have them in the direction of your longer-term project. But on many occasions we have gone on sideways, and we did some experiments which were not aimed at in this direction. For instance, we studied the interaction of Rydberg atoms with each other, which was a nuisance for our final goal, but which provided results which have become important because other people have decades later come back to this and have developed this also in their own direction to do interesting things. So you have to do both ways, but not, of course, you don't have, if you have an artifact, you should not just dig into the artifact. You have what you do on the side must have its own interest.
Here, thank you very much for your presentation. I have a question because after your presentation, I can realize that the science are ongoing to the details that are difficult to the normal people can understand. So what you can recommend to do the science more close to the people? Did you understand?
You mean to make your science understood by laymen, by people who are not scientists?
Well, we have a problem in the science because the people cannot understand too much the science.
Yes.
So the government want to decrease the
I think.
The budget.
Okay, I understand you.
So how we can do that the science be more close to the people?
The problem is at different levels. I think the people don't understand, but the politicians don't understand also. And so I think you have to educate, and first of all you have to educate students, you have to educate young people to make them understand that science is important by giving examples, by talking about the history of sciences too. And then if you are a successful scientist, I think it's one of your duties to explain to other people, to go to talk to journalists, to talk to people, to go in schools and to talk to students. I think this is important if you want to convey the idea that science, as I said in the end, that science is the place where truth is defined. You already have to understand that and to make people understand that. And I'm worried that when you have many problems, such as the problem we have today here, is that science will be completely forgotten. And this is a big problem.
Hi, thank you for your talk. So mine is a broad question. I watched a documentary which deals mainly on how quantum physics influences philosophy nowadays, in the sense that because you can assign a matter to your thoughts, then the consequences of your own life are directly impacted by quantum physics. I don't know if you have any thoughts or comments on that, or how all this, as you said, the differences in this physics, in this very microscopical differences, impact more in a philosophical kind of way.
Okay, there have been a lot of course, discussion about the philosophical implication of quantum physics and of relativity too. And a lot of things have been said which I don't agree with. That, for example, that you can understand the mind and the free will because of the indeterminacy of quantum physics. I think it is just a wishful thinking. I think that there is no direct connection between that. I think the behavior, the brain is a soft and warm system, and quantum physics, the domain of quantum physics is cold, low temperature, which is completely different from what happens in the brain. So I think these ideas, metaphysical ideas, which are based on a kind of fuzzy conception of quantum physics, have to be taken with care. Now, of course, all is quantum at the bottom. Atoms are quantum, and molecules are made of atoms are quantum. The DNA molecule is quantum because the links between the atoms in these molecules are quantum. But quantum is not enough to explain the emerging properties of life, I think. Even for the simple life at the level of cells, but even more at the level of complex systems. So the connection between quantum physics and life is a very complex thing, and one should not say very simple and confusing things about that.
Hello. You talked a lot about precision measurements,
Yeah.
and how you can make measurements at 10 to the minus 18 precision. But how do you deal with interference? So working at the Collège de France, you have the metro. Maybe the metro is making your laser vibrate slightly, or the cell phone tower is emitting frequencies, etc.
You have to protect the system from perturbations, and you do it at an exceedingly high level. You take the example of the metro, but if you look at the gravitational wave antennas, you have huge mirrors separated by 4 kilometers, and you look at the displacement, which is 10⁻18 meters, which is, as I said, 1/1000th of the size of a single atom. You have to protect these mirrors from earthquakes, from cars, from all those kind of things, and this is a miracle. It's not a miracle, but this is really the tour de force of technicians. It's a tour de force in mechanics. You have to isolate the system from vibration, and the tour de force of electromagnetism, because you have to produce coherent waves which don't skip a bit when the light is propagating from one mirror to the other. So these are really tour de force experiments, much more difficult and to measure with 10⁻18 precision of a spectral line. The same, you need to have a laser stable to this precision, and so the laser are suspended in quartz threads to isolate them completely from the vibrations that you are mentioning. So it's really a kind of a lot of tricks which are used, a lot of expertise, a lot of wizardry to reach this kind of precision. But it can be done.
Hi, thank you very much for the talk. As you mentioned at the end of your presentation, the good law for being a good researcher, how do you manage the doubt when you, during the past decades, when you did your research, did you ever think about quitting research or? Thank you.
No, no. I think the conditions were easier 30 or 40 years ago. At that time, the CNRS had more money than it has now. It could fund an ambitious project over a long period of time. And when the things became tighter and when we started to have to apply for grants, I was already well established and it was relatively easy for me to get the grants. But nevertheless, so this is one point. The other point is that at some time you have problems, of course. Experiments don't work, either because you choose the wrong path or because you had an accident in the lab. It happened that at some point we had an accident with a cryostat and it took us back for 1 year or two. And this is, so you don't have to lose faith and patience in that case. It helps to work in a group as an experimentalist, because then you can just discuss with each other, and if you have a good sense of humor, you can relativize, you can took bad events with some kind of good spirits. So maybe it's more difficult for a theorist who works alone and who can be more prone to depression if his work does not work well. But as an experimentalist, and also, I must say also that we do in the Pasteur lab, we did at the same time theory and experiment. We tried to develop the theory of our experiments, so when we had a big drawback in the experiments, so we took our time to think about the theory, to write papers, to explain what we were going to do, and so on. So, but until the end, until we get to the last result, be able to see a single photon, we are not sure it would work. It relied on the possibility to get an exceedingly good cavity, and this happened as a big surprise. It was expected because that's what we wanted to do, but the odds, if I had been asked what are the chances, I would have said maybe 30%, 40%. And this is the same for the Nobel Prize, because there are a lot of very good people around who deserve a Nobel Prize, and only a few which are being given. So it's largely a matter of luck, and I must tell you, don't work for that. Just enjoy what you are doing, and this can come or not come, and it's not directly related to your own value, and even to the value of your work. In physics, I know not a lot, but I know many great physical results in physics who, for one reason or not, did not get a Nobel Prize.
Thanks for the nice talk. So my question is about research in academia versus research in the industrial world, such as big IT companies, Google, IBM, because nowadays you can read a lot of news like a quantum computer they are making. In a few years, you will get a quantum computer on your laptop or something like this kind of news. So could you comment on the fact that, is the industrial world are leading in fundamental research such as artificial intelligence and quantum computing?
Okay, artificial intelligence, I don't know. I think the big companies like Facebook and others have huge research program in artificial intelligence, and they are driving the progress in this direction. As far as the quantum computer is concerned, Google and Microsoft and IBM have programs. They spend what would be for us a lot of money, but what for them is nothing. And they do that as a kind of, I don't know how you say in English, very scientific, just to decide, just in case it would work, we have to be in the business. And at the same time, they oversell. When they get a very small system with a few qubits and they pretend that this is the first step for a quantum computer. So there is a lot of hype, a lot of competition between them, which leads them to say things that you don't write in a good scientific paper. So I don't want to say that it's not good that they are doing this research, but you have to understand what is at stake. And all the great, of course, I don't know what is classified, but all the results which have been published in the quantum computer in good literature come from the academic world. Maybe there are things that they don't publish elsewhere, but then I cannot comment about, and I don't think it's a good strategy for research anyway.
I'm very sorry to stop this very interesting discussion between you and the students, the former students. But I invite you to meet with Professor Haroche at the end of the ceremony to discuss further, and we pass to the next step. And the next step is again to thank you so much, Professor Haroche, for your